All right. So this week, have you guys got a chance to implement DDPG by any chance?
A little bit.
Mm-hmm.
No,
Well, what was your name? I forgot to catch that.
uh, my name.
Your name is my name,
My name is Lucas.
Lucas. I gotcha. Yeah, Lucas. Okay. This week I did a little implementation, and I was kind of surprised by the fact that it just kind of worked. Let me see where I can find the file.
Yes, so it is actually very, it's very simple algorithm. So it's a pity that I didn't make it, but yeah, it's very simple algorithm at the end of the day.
Yeah. Did you try?
Well, I tell you what is my problem is that I've seen many different implementation,
Uh-huh.
and of course, what I would eventually do, I would probably copy it, right?
Right.
Even unintentionally, that's what I would do probably. So,
I see. I see. Okay.
uh,
Yeah. I see. Maybe it would be helpful if I kind of share my experience with my implementation to maybe give you a sense of. So, of course, I did some copy and pasting, but I also feel it was a good balance between copy pasting and writing original content myself. Um, so before I guess before we talk about the code itself, let's take a look at the results. So for the pendulum, uh, it takes a long right. It actually, if you try.
are you sharing your screen right now?
Oh yeah, right. Sorry. Let me do that right now. You guys see?
Yes, we can see.
hmm so I just want to mention that for pendulum, before we talk about code, let's look at the performance. And I just want to mention that for pendulum, the algorithm is actually able to learn much faster. The reason why it takes 2 million frames to learn is because the exploration strategy that I post upon it. So I use the epsilon greedy exploration, and even at the end there's still 5% a chance to do random actions. That's why it's performing very poorly. But if you see the reward, you can usually see some really good reward, like negative 100, but sometimes it's doing very badly, like negative 3000. But overall you can see that it definitely learns. And I ran this experiment also on hopper end as well. And this one, I mistype a number. Instead of 2 million, I type it 200K. But as you can see, the agent still was able to learn quite convincingly. So now let's get into the code. And I think it would be also helpful if I kind of point out the different things that I did when I was doing the implementation to again to sort of give you guys a sense of maybe the amount of copy and pasting and the actual implementation that you would do. Of course, the thing that you always want to do is to, of course, try to write the implementation yourself in the beginning, but it would be also very helpful if you check out some other people's code. So, for example, I checked out the OpenAI spinning up its implementation on the DDPG, as well as the minimals RL implementation. I think the first thing that I did was to copy the DQN file, because the DDBG shares a lot of common characteristics such as the replay buffer and the Q function. So I copied the whole thing into the DDPG file. And then what I did was to modify the Q network and the actor network. The reason is that the Q network is a little different, because now instead of generating all possible Q values for all the available actions as it is in the discrete case, um, it might be helpful if I sort of show you side by side.
Okay, so to make things clear, you
So
based yourself on DQN and then upgrade it to DDPG. Is that
yes,
it?
yes,
Okay.
exactly. So if you notice here, the original queue network for the discrete action space, what you would do is you generate the queue values for each available actions. And then essentially you're asking what's the actions that will give me the best queue values. And that's how you do the action selection, do the target bootstrap, and do the update and all that. But for the queue network in the DDPG, since the number of actions is not enumerable, you actually put the actions as part of the inputs as well. So that's the first modification that I had to make, which is notably very similar to which is essentially the same queue function as the software actor critic, because software actor critic also takes in the action as well as the observation and generate a single value for the queue function. And now I have so many tabs open. And the second thing that I had to do was to sort of look at the actor. And this I did copy and paste because I feel like this part is fairly straightforward. Not much to read into. I copied the MuteNet from the minimal RL implementation and just rename it actor. And everything is very straightforward in terms of what it wants to do. And then I initialize the target network as well as the target network for the queue function as well as the actor. And then, so this is one of the things that I do a little differently than the implementations above. So first of all, the DDPG implemented by the minimal RL, they use the Ornstein Uhlenbeck noise. So that's the original implementation.
I just have a quick question before
Yeah, go
you
ahead.
continue. When you define the policy of the agents, after you apply the batch activation, I see there is a mu in the line 162. Mu equals storage times and the times and action space I.
Yes.
So what's happening there?
Like the putting a 10 around it.
After when you multiply it by the minimum of the
right. Yes. So so when you generate a single value for the actions, right? We use 10 to squash it into the range between -1 and 1, right?
Yes.
And then we multiply by the scale of the actions, the maximum of the action space. So that's all there it is. But I take the minimum to avoid the bug that. So imagine if you have the action space and then the high looks like 2, 3, 4. Like the maximum scalar value for each action is 2, 3, 4. And then it's possible if you just multiply by the action space out high, it's possible that the first dimension you generate a value of 4 when the highest value should be 2. So that I just take a minimum of those. So it's a minor detail for the easy.
Okay, but that's a kind of lazy approach, I would say.
Yes.
But I get the idea now.
Yes, I think the correct idea is.
I think since the result of torch 10 is a vector which has the action space dimension, right? And action space high 2 is has the same dimension. So by doing the element-wise multiplication, we should have already the proper action in the correct range outputted.
Oh, I see what you're saying. So instead of doing times minimum of that, I should just times itself, right? Something like that.
Probably. It depends if Python actually does the element-wise.
Right. I see what you mean. I'll investigate to make sure. But that's actually, that's a very good idea, I think.
Okay, I get the idea. Yes, thanks.
Yes, very good idea. Let me just do that so that I don't forget.
or maybe add a to do.
Yeah. Check if tensor this element-wise multiplication with numpy array, which I think you probably have to do something else. But anyway, let's take a look at something else.
You were Ornstein-Uhlenbeck noise description.
Yes, so they generate the noise by the Ornstein-Uhlenbeck noise, which we looked it up. We looked it up last week, and we weren't able to find an exact source for the implementation. And I was also looking at OpenAI's implementation for the noise, and they also kind of do it differently. So the way they do the noise is a simple Gaussian noise, which is kind of what I did in the end. So they generate the action plus the action noise times a random variable sample from the normal distribution. And if you look at its implementation strategy, its exploration strategy is that if the current time step is greater than some starting time step, then you generate the action by getting the action from the mu and then adding an action noise. Otherwise, you randomly sample from the environment. So my implementation, I was like, well, I could do an epsilon greedy exploration, right? It's a standard DQN approach. If the random value is less than epsilon, then I randomly sample an action. Otherwise, I do the noise thing that is presented in the DDPG implementation of OpenAI's repository. And that's why the pendulum takes so long to solve. Is because of the fact that I set the exploration time to be too much, so that the epsilon is very high. So to solve pendulum better, I could just simply set the epsilon to go down a lot faster than it is in the current case. And anyway,
I think there is two concepts mixing over there.
Yes, go ahead.
First, with the start step, I think the idea was to get enough samples to actually have an accurate enough estimation of the Q function. Mm-hmm. So when we stop agents upgrader, we get some good result instead of agent wandering in 10x. Mm-hmm. But when it comes to epsilon itself, I think it concerns the exploration of the agent itself. So shouldn't we separate those two?
Right. One is more systematic. The other one is more like on the lower level for the action generation, right?
The epsilon is the later, right?
The epsilon is for the systematic exploration, right? And the noise is for individual action selection. But perhaps
epsilon has nothing to do with the noise. Okay, I see. In this case,
but perhaps that's not really important. It's just different ways to do exploration. The other ways to do the exploration that I've seen is to instead what you would do is they also use the Ornstein-Uhlenbeck
let's say
noise.
OU for now.
Yeah. Let's say OU. They use the OU noise, but they have some sort of annealing process so that the noise becomes smaller and smaller. And with the Gaussian exploration, you can just as easily to apply an annealing on the noise scale, like the 0.1 goes from 0.1 to 0.0001, something like that. I think it's just some sort of exploration strategy, and I don't think it's that important, I guess.
Okay, let me explain you intuitively how I feel about the epsilon epsilon based exploration. I guess by default we are expecting the agent to explore because of the noise that is added to its action, right?
Mm-hmm.
But if on top of this we add the epsilon, let's say the agent has already trained 500 epochs out of 1000, and its goal, which was to maybe run over 100 meters, he can already go halfway. And then since the epsilon kicks in, it's not, if we just use the noise action, once he does the half of the way, he now starts to explore around that middle part of the track, right? But if we do random exploration, even though the agent already knows how to, like, wait, it's every time step you do this.
Yes.
Okay. Sorry. I guess it's
the other thing. Yeah. The other thing that I would think might worth noting is that the action space sample, it actually could be a lot. It probably has more variance than the action noise, because action noise is very small, but the action space sample could be very large.
In a sense, it's a good thing. Okay, I see the idea now. Thanks.
Right. Yeah, not a problem. And let's take a look at training. So this is kind of where things, I guess, get a little more interesting. And I have the DQN training part on the left, so that we can, the DQN on the right, so that we can have a comparison of what looks different, right? So you still sample from the replay buffer. So these part of the code is the same. However, in the DQN, what you want to do is you get the maximum of the target value given a next state, but that's not the case with the DDPG. What you would do is you generate the actions given a next state, and then you find the Q values based on those actions. So in a way, the target Q would be equivalent to the target max, right?
Target Q?
Yes, because the target, because you're generating the next state actions, and you're assuming the next state actions are sort of the optimal ones, I suppose. And then that's why I think they're very equivalent to the target max, because you're kind of similar, right?
Yes.
And then you still calculate the TD target, which is very similar to rewards plus gamma times the target max, and over here is target Q, and then minus the dones. If it's done, then there's no future rewards. And then you also have the old value. This is also a little different. So for the old value from the DQN side, because of the parameterization of the Q function, you essentially take the actions index and gather the Q values that are used to make the action selection. However, in DDPG, what you would do is you just generate the values directly, because the Q network takes in the observation and the actions themselves, right? And then you define the Q loss as a temporal difference that's similar as well, and then you optimize the model. The TD part is very similar. You just do the loss directly backward, and then you step from the optimizer. However, on the DDPG side, you also have the update from the actor. And the actor's loss, which is this line that is not presented in a DQN, is to essentially maximize the Q function given given a current observation. Notice that it doesn't use the old actions. However, it generates new actions. So that's how it gets its gradient, right? So that you can do the update on the actor. And the final difference is how you update the target network. Over here, you do this hard update to some frequency, but here you're doing the soft update every step. And that's about it for the DDPG implementation, and it works quite reasonably well. well, I need to do more comprehensive benchmark to get a feel of its performance. But I was hoping that we could talk about the implementations and maybe something that I could change, perfect before we run it on the in the big league, right? So.
One question, will it be possible to use it for discrete actions space?
So I was reading this post online about if DDPG can be applied to discrete action space, but it almost sounds like the kind of the conclusion that the people in the posts had was that if you want to deal with a discrete action space, it's much better to do DQN. DDPG, the fact that you're doing all those things, like for example, selecting the just randomly select an action and then get the Q values that way, is really in a way not as good as just sort of generate the actions and select the actions that has the best Q value. So in a way, this part of the DQN code, so if you compare this part and this part, the DQN's part of the code is more superior because here is sort of an approximation. And but
It's approximation, but
maybe it's
yeah,
better.
it's better. Yeah.
We can definitely try. And I don't think there's gonna be any challenge on the. Actually, is there gonna be?
But what would be like approach, to do this, like using a softmax over, from the output of this first neural network?
Yeah, that's the thing that I'm not so sure of. Like you could generate a logits and then select the actions with the largest logits, but at that point, I feel like it's just gonna be very similar to DQN. Oh, actually, in fact, that would be the SARSA, right? The That's what SARSA does. So over here at the DQN, you get a target max, which is the maximum over the actions. However, in SARSA, you're only getting the Q values and the actions. And then if you had implemented the actors using selecting the logits with the largest value, and then notice you're getting the next state actions based on the actor, I think it would be essentially the same as this, right?
I do not think so.
You do not think so? Okay. Because the AT plus 1 would also be generated by using the Q function. Generated according to the Q function. And then if we do that, then this process would be the same, and the way you calculate a target would be the same, and everything else would be sort of the same. But you would have to do this, right? And how you optimize the actor. So that might be the only thing that's different.
Yeah, because we still have like a chain of neural networks, right? So one input of one goes to another.
Right. The only difference is that if you apply, it will sort of look like SARSA, but you would have to separately optimize over the actor.
I would say it depends on the nature of the network in that case. But if the network is deterministic, as in DQN, right? Because basically it just outputs the probability and always takes the argmax. We do not have a distribution.
Yeah.
But in the soft actor critique, I don't know if you remember, the policy is actually a categorical one. So although we have the logits and the corresponding probabilities, it's not always the max action that is sampled.
Right.
There's bound to be a slight difference. And I think that's what someone posted in the Slack. Who was it?
Martosa. Probably.
I think it's Thomas Erva.
Oh, never mind. Yes.
I think it's the same the same topic we are discussing now.
Mm-hmm.
What happens if instead of taking the max, we instead take the expectation computed using the policy and the Q value?
I think it's different. Thomas Merva is talking more of replacing the Q function with the value function, right?
But the concept is exactly the Q learning versus SARSA. No? Okay, I think SARSA is a special method for continuous case. Yes?
I'm not sure, but I think it's definitely worth playing around the discrete action space and see essentially what we can do with it.
Mm, yeah.
So, Rosalind,
Also,
go ahead.
regarding to, can you scroll back up on your DQN to the policy network, please?
Yeah.
The policy. I mean the agent. Okay, that's it actually. So that's the policy. I see. In that case, never mind.
Right, because if you're dealing with discrete action space, you couldn't just map the state into actions. You have to either select. You have to have like a selection strategy, something like that.
What I was thinking is that on top of the self FC3, right, we could have something like, well, the FC3 is basically logits, logits layer.
Yes.
We pass it categorical distribution.
Yeah, we can.
And we do not need to use epsilon for exploration anymore because the distribution will take care of exploration through the sampling process, if I'm not mistaken.
Right. So that would be sort of a combination between the policy gradient kind of styles exploration versus, and then but still somehow using the DQN.
And
yeah, it's pretty interesting.
On top of that, we could have a more accurate estimation of the targets we use to update the Q network, because we then multiply the whole probability vector times the actual values. Wait, does it make sense?
That part doesn't. That's from the SAC, right?
Yes.
Yeah, that part doesn't make sense. I always didn't quite enjoy that part, but can definitely look into it.
Okay, maybe one day.
Yes. Right. Do you guys have any other questions or comments?
I remember in the original paper, they had mentioned something about the batch.
It is a batch, right? Because you're sampling from the replay buffer.
Okay, I meant a batch normalization.
Oh, yes, indeed. That would be a technique that I didn't implement. You're absolutely right.
I am curious of where does it happen? The batch norm.
I think it's when you sample it from the replay buffer. So what you would do is you're normalize the observation, right? Do you have the paper? Do you have the paper? Never mind. Let me look it up real quick. Right. This technique normalizes each dimensions across samples in a mini batch to have unit-means and unit-mean and variance. So I can only imagine that's talking about the sampled observation, because it doesn't make much sense for actions, rewards, and the dones. You know.
Okay.
Yeah. So that would be another thing that we could check is to. Oh, not here. Oops. to do. Implement the batch normalization. I'm also kind of interested in knowing if the OpenAI guys, they did the batch normalization. So that would be something like the STD. No, they did not, I think. Right? So where did I train?
But I
Compute
think
loss.
you're looking where the update function is called, because that's where they pass the data.
I found it. So they sample from the observation, and they don't.
Oh, yeah.
They don't do the. I don't think they do. Where's the replay buffer? Sample batch. Yeah, I don't think so. You see, it's just selecting the indices. It doesn't do the normalization. That would be something like a flag that we can turn on and off. And I believe minimal RL also doesn't do that, right? So if you look at their replay buffer, yeah, there's nothing special about it. And when you actually train, yeah, there's no batch normalization. I wonder if it really has a significant performance impact.
Okay. I think you were right. I found the part where they said that they only normalize the inputs.
Oh, did you? Where is it?
Page 4.
I'm looking at your screen right now, so if you could just highlight it.
In the low dimensional case, we use batch norm on state inputs.
Okay.
And they say also all layers of the new network. So now I'm confused because I remember in PyTorch there is this
batch normalization. Right.
So that one, it normalizes the activations. Is that it?
I remember seeing it, but I at the time I thought it was something related to the like convolutional layers and stuff. Like computer vision people sometimes do that. So I'm not entirely sure what that does, I guess.
Maybe they use it to. Oh, I see. So between the two layers, for example, if you have two layers and the logics of the first layer gets too high, it might impact the result of the next layer. So they use batch norm to bring it back into a reasonable range.
Oh, I see. Okay, that's a simple idea.
And maybe that could actually help alleviate the problem of exploding logics in PPU.
You know what? I think that's a good point.
I am not sure because there are norm 1D, norm 2D.
Yeah, we have to look into that. But I think people usually don't do that, right? At least for the RL, yeah. At least for the RL community, I haven't seen that very often. It doesn't seem to be a very popular technique, let's say. So if I look at, for example, the OpenAI's implementation, yeah.
Yes, we pure MLPs.
Yeah, it's like, you get so irritated. Where is your MLP defined? Huh? NMLP. Oh, okay, right. It's just a bunch of linear layers with 10 H. Yeah, there's definitely no batch normalization in their code.
I'll try to keep that in mind.
Yeah, that would be. Yeah, that would be something interested in to look into, I would say. Yeah. Do you guys have anything else to add for the DDPG?
A moment, please.
Hmm. Take your time.
Do you use a target policy network to generate the next news?
Yes. One way or the other.
Okay, actually, I see. In soft actor critic, I noticed they do not use like a target network when they generate the next log file. I actually tried to implement it, but it doesn't change much anyway. So I guess that's that.
Okay.
Okay. So another point I wanted to bring up this time,
Uh-huh.
it's quite general actually. So I was wondering, as I think in DDPG you have something like okay, you use epsilon to decide. Oh wait, do you have an argument like start steps? Like before starting the update, we use a purely action space dot sample to
Hmm.
fill the buffer up until a certain threshold.
So I think that's fairly random. It's probably trial and an error. I don't think there's like a strong argument for for exactly how much you should set.
No, I'm not talking about the quantity. I was actually wondering if we should include those steps into the learning steps, because at that point the agent is not really learning yet. So
Um, it's a good question. I don't know. I feel like yeah, I feel like this is one of those things that it feels more of tuning than actual science, if that makes sense. Because
yes, also since they're usually quite for example, they say start step at 10,000, but we train over maybe 1 million, so it's not really that important indeed, in
right, right.
retrospect.
It's like the KL divergence bounding that feels more like hard science because you're enforcing something and that turns out to be important. But this is more different exploration strategies you can sample. I don't see how one exploration strategy, if tuned well, could be categorically worse than other exploration strategies.
Mm, mm. Okay.
Yeah.
A little bit of a segue into twin delayed DDPG.
Okay. Do you have a?
But,
Did you already implement that or?
actually, I did. But
Oh,
anyway,
nice. Okay.
well, as you said before, the OU noise stuff is actually not that important.
Okay.
I think they did quite some extensive experiments in that paper. And
Really?
on top of that, they used the next views are also noise. They also apply some noise to that.
Oh, really? Interesting. Okay.
Yes. So I was wondering what will be the impact on simple DDPG first.
Yeah, I have no idea, man.
But I was waiting if you would implement it in your version.
I can definitely implement that. Like a lot of those kind of questions are the kind of things that I feel there's no intuitive answers to. You know?
In this case, it's more about fine tuning too, I guess.
Right, right, right. Exactly.
I see.
So, when you implemented the DDPG, was there some part of your code that looks very different than my implementation?
I do not think so.
Okay,
It's pretty much the same. So
I see. I see. Okay.
yes. Mm, I guess it's just the details. But when in your code you said the old values,
Uh
I will say it's more like the current estimate. It's not old yet.
huh. Right, right.
So, and maybe it's a really slight difference, but I think I resampled the actions. Wait. Could you bring up your?
I think that's the
your
same
edit-
when you calculate the when you calculate the Q loss, right? It's the
Yeah.
same. Because over here I do generate new actions.
Okay, so that's the same.
Yeah, that's the same then. All right. Okay, then I would say for the most part it's very similar.
Yes.
Mhm.
Uh, have you had any chance to read up the parameter noise
Aha.
space exploration paper?
I have not. How's your experimental results on this?
I think my the implementation is really bad.
Oh, okay.
It's really naive. I actually did not read the paper itself to see how they do.
Okay.
I just get the idea that you apply the noise on the weights of the neural network,
Really?
and that yes, directly.
That feels
It's
so
so
random. It's like there's no intuitive answers as to why it would work well, you know?
uh, it's something about correlating the noise, the resulting action from the network itself.
Okay.
But yes, that's an intuitive approach, I guess. I should do due diligence and read the paper properly.
Yeah, if I had a chance, I'll definitely try it out as well.
But it sounds like a detail. I think is there that much of performance improvement?
Mm-hmm.
Let me.
I see.
Okay, they say medium DQN returns for several, and the parameter noise the proposed is in blue. It seems. Okay,
Okay, this is DQN, right? Okay.
that's DQN, and they add the parameter noise for exploration instead of
That's
direct.
right.
Okay, in this case, boundary.
That's very interesting.
Besides some environments, it doesn't seem to actually improve very much.
I can find some intuition as to why some sort of more structured exploration would be better. Because Epsilon greedy is a very stupid exploration, to put it bluntly. If you're more specific about your exploration, like if you somehow correlate your actions and then you know where you are, and then if you have some sort of sense of where you should explore, I think it might actually help with the explorations, because some explorations is purely pretty garbage. Um, but yeah,
Okay, maybe I will look into it later.
yeah. If I have a chance, I'll definitely look into it as well. So the other thing that I want to quickly mention is that recently I got into AWS Batch, and I'm trying something out to try to see if we can run a lot of experiments at once. So, by the way, the Ali is going to do a presentation on Azure Shipyard. It's very similar to AWS Batch. Essentially, it gives you a way to run a lot of experiments at once, distributed across a bunch of different machines that you have. And the reason why I find that attractive is we found this AWS black market that you can have 5,000 credits for just $400. I think it's a pretty great deal, and if I have it, then I think running a lot of experiments maybe it'll be a lot faster. And AWS Batch, the way it works is that uh, let's take a look. So you define some sort of computing environment, and then you specify the maximum number of CPUs and the minimum number of CPUs. So if you have no task running, then there's no instances of running up. However, if you have instances, it'll help you to determine the number of CPUs that it'll spin up and the number of memories. so that the computation is the cluster management is sort of being managed by AWS, and then you just submit jobs in the form of Docker container. So I've been kind of playing around with it.
Interesting.
Yeah, and if you think about it, and the other thing is, it can be a lot cheaper if you use AWS Spot instance for the EC2. Those are instances that can be terminated if AWS needs its computational power back. So if we use that to run a lot of experiments, it could be like up to 80% cheaper as well.
Wow.
And then if we buy the credits, which is like another 90% off, then I don't know. It probably means that if I run experiments using that AWS credit, it'll probably be something like 95% off or something crazy like that.
Interesting.
Then I think it would actually make sense to run a lot of experiments at once. So for example, we have the benchmark SH, right? I never reran it because it takes so much time. But if we have the AWS, the batch jobs, then all I need to do is just submit the jobs and it'll do it for me.
It just might take a while, right?
Huh?
It might take a while.
Yeah, it might take a while, but supposedly it's faster than if I had run all of these things on my computer. Like my computer has 24 cores, which is pretty great. But if you have hundreds of experiments you want to run, in this case for the benchmark, you have, I don't know how much we have. Let's see. We have 45 selections, and 45 times 2 is 90 experiments. Really? I thought we would have more. But anyway, let's say we only have 90 experiments. Really? Okay, never mind. We have 90 experiments that we want to run, and then it definitely needs to be run in sort of a batch style on my computer because I don't have 90 cores. I only have 24 cores, so I have to separate them up, and it's a lot of effort to do that. Sometimes, at least, I guess. But if you're using the AWS batch, I feel like you could just submit them, and then it'll sort of dynamically provide you with the computational power. And once the job are done, it'll just return it to you. It'll just terminate those instances, so you don't incur any extra cost. So I feel that would be a pretty good thing to have, especially in the sense that it gives us the theoretical possibility of running literally thousands of experiments at once, right? Because we can just submit jobs.
Indeed.
Yeah, so I think that's pretty cool.
It's good. There are such. So there's basically two methods to make it cheaper. Use the batches and like a free AWS
Credit?
nodes and the discounted credits
Yes.
on top of.
Yes, exactly. All the ways to get computational power, right?
Deep learning.
It's just surprisingly cheap.
Yeah, I know, right?
When you combine, maybe it's intentional, right?
Yeah, just because of that credit thing, I might spin up all of my instances on AWS. Right now, I have an instance in an EC2 instance. Oh, the other thing, yeah, there's a bunch of savings you can do. Like, instead of doing it on demand, you can also pre-purchase.
Yeah, you can pay in advance, right?
Yeah, you can pay in advance, and it also saves like about 60% or something like that. Saving plans, yay! Says something like Right. You can computing savings costs up to 66%. Right. So that's pretty cool. So yeah, that will be an additional savings on all of the saving techniques that we thought about.
Good to know.
Yeah, good to know. All right. Do you guys have any other questions or concerns?
Yes, unfortunately, I have one.
Okay, go ahead.
I had a kind of a quiz style question for you.
Okay.
When you use the PyTorch nn.linear layer, right?
Yes.
What do you think is the initialization method
I think
for the weights?
it's Xavier, right?
It's not Xavier.
It's not really.
It's not. It uses something like a uniform distribution over the square root of the inverse of your dimension.
Really?
The number of, yes.
That's very interesting.
Yeah, but it was very popular technique.
Yeah, I bet
But
they
I
did.
think in the reinforcement learning field, we use Xavier, right?
Yeah. Mm-hmm.
In some of my experiments, I noticed that there was a drastic improvement in performance when I actually used the Xavier instead of the default
Really?
initial scheme. So now I
Okay.
am reworking most of the neural networks to add the custom initialization.
I see. I see.
So
That's pretty interesting.
I think this is where they do it. If you check on my screen, they use
Oh, I see. I see. Huh.
where is this? Oh, come on.
You're right. That is pretty interesting.
So
Yeah.
that was something we took for granted in TensorFlow.
Yeah, that's very interesting. I wonder. Yeah. Yeah. Anyway.
So pay attention.
Yes.
I actually have some benchmark of DDPG on I think 5 environments. Well, it basically works. In Hopper, I think a SAC is still the best. It averages around 200, 2500. Sorry.
Okay.
This one is half cheetah. I think it will be interesting to compare it with. How do I do this?
Different noise. You mean?
Not the noise, but with the TG3, which is probably laying around somewhere. Wait. And while we're at it, does anyone know how to customize PyBullet environments?
I have no idea. So that's why I think Unity, at some point, if they do it smartly, they'll take over.
I don't know if you have seen the maze environments with ant and such things in the Mujoko. There's like a maze, and the agent
Really?
has to like navigate it and take some stuff, right?
Right.
So I was wondering if we could get a similar one in
Yeah,
PyBullet.
I have no idea. You probably have to dig into their source code to see how that's defined.
Okay, I guess I have no choice. So yes,
Yeah.
DDPG against the TG3, but the nature of the algorithm is basically the same, but well, we can see big performance jump here actually. And if I could manage to get it to learn so as smoothly as your version, I
Right.
think that would.
Yeah, they all seem very unstable. That's interesting.
Well, at least it works.
Yeah,
I
yeah.
could not.
Yeah,
One
I definitely think they learn. So that's good.
Walker and finally humanoid. I don't know if the score is supposed to be negative. Probably not, right?
No.
Tough actor gets at least 60, 100, something like that. Okay.
Right. So there's probably some bugs to be fixed.
And tell me something, guys. Are you using like your local computers to train these agents?
Which one?
All the because it's all this environment requires like a lot of computation.
Well, we have servers in my lab, so I
Okay.
use them.
Okay.
Yeah, I also use servers in our lab, and we have the servers in our lab has a lot more cores, but its cooling is not that good, and if we run a lot of experiments, the fans go crazy, and you can hear in another room. So you see 86 cores, but I don't feel comfortable using all of them.
Boy, I'm jealous.
Yeah, but the time that it's like if I use all the cores, you hear the sound of like literally that loud.
Well, it's the same for me, just that the servers are in a different room in the basement, so there's no such problem.
Right.
Yeah. Well, I'm waiting for Bitcoin crash.
But if we have the AWS Batch, we don't have to worry anything about that. Assuming it's fairly cheap. I want to test it out just to see what will be the cost if I run, let's say, 10 experiments. If it's like, I don't know, like really cheap, like 1 cent or something, I think it's probably worth it to just for. I mean, we can obviously still use the servers for computation, but I feel like it'll give us more flexibility.
Is it faster than when you use your own servers?
I haven't tried it out. I'm still trying to. I want some sort of interpolation that I can generate the jobs from the bash scripts, but that's a little bit difficult. There's some issues with Docker that it doesn't accept the sort of multi-line things as the commands.
I see. Unfortunate.
Yeah. Yeah. Oh well. Do you guys have any other questions or comments?
Just so the next one will be as well, devoted to DDPG, right?
Yes. So for the next week, we'll be again doing implementations, trying out different things. So one thing that I might try to do is to compare the performance result with the batch, with and without the batch normalization.
For me, it feels like it's really environment, dependent, right? I think because
Probably, yeah. But yeah, and also we can look at different exploration strategies and
maybe this discrete thing,
yes.
I do not get this idea, but that would be kind of like interesting.
Yeah, I think so too. That would be another thing that we can definitely look at next week. But yeah, other than that, I think that's our plan so far. All right.
Great.
Yeah, great. Thanks everyone for coming.
Yeah, thank you.
Yeah, thank you. And I'll see you guys next week.
Yeah.
Have a good weekend. Yeah,
Thank
sounds
you.
good.
Have a good weekend.
You too. Bye bye.
Bye bye.